recording software. And I'll start. Let me see. Can you hear me in Discord? I think you can, right?
I can, yeah.
Okay, cool. I can, and it sounds like normal. It's not like awful audio. Because I'm taking it as it's probably good. Because before it was really bad. Okay, let me go ahead and share my camera with you guys, and then we can go ahead and get started. Okay, cool. So, what questions do you guys have for me?
Question 3.
Of homework 7. So which one was that one? That was the... Oh, that was coding in System Verilog. Okay, cool.
D.
Part D?
Yes.
Okay. So here's what I'm going to do. I'm going to... Yeah, no, that's good. So what I'm going to do, you can join on the Discord if you want to see my screen, because I'm not going to write the Verilog up on the board. I'm just going to type it up. I'll share the screen with the Discord, and you guys can see it at the same time. So let me do that. Pen. Let's do this. No capture, no pad. Okay. All right, cool. So I'm in the recording. It's just going to show up as the notepad itself. But I'll go ahead and share my screen on Discord, and you guys should be able to see it right on the video. I'll do it here. That might be a little better. Order, move to top. Okay, cool. So I'll go ahead and start off by taking a look at that first set of code, or the first prompt, which was 3A. So I talked about this a little bit during the last office hours, but I'll go over it again. So what does this module ask you to do? Okay. And what is it going to do? Let me go and take a look. I think I might have done a different problem last time. Oh, you're on D. Okay.
Yes, D.
Okay, cool. Does anyone want to start earlier than D? Because we can start at D, I don't mind, or we can start at any of the other points. So does anyone have a preference?
I'll say B.
Starting at B? Yeah, we can start from B. So, does anyone want to see A? Because if you don't want to see A, then we can just skip past it. Okay, yeah. Yeah, or just actually do the entire homework, Victor. Okay. So here's what I'll do. I'll go ahead and start typing up the code. So remember that whenever you have a module that you want to make in System Verilog, you start by saying module, then the name of that module, and then in the parentheses, that's what's called your port list. You can think of the port list as just the things that are coming in and out of your circuit. So the terminals or the ports, that's why it's called the port list. And so for the first part A, what we're asked to find is we're asked to take in an input, which is a 3-bit value A. So what I'm going to do is I'm going to write that in here. So I have input logic, and then I have to specify that it's 3 bits. And the way I do that is I say 2:0. And that's how I specify a 3-bit signal, because you have bit 0, bit 1, and bit 2. So that's 3 bits in total. And I'm going to call this A, just because that's what they said on the paper to use. Cool. Next thing I'm going to do is I'm going to write my output logic. So for this, they asked you to output a value y. So I'm going to say output logic, and then I'm going to put 11 to 0. 11 to 0 because from 0 to 11 there's 12 bits. I'm going to call that y. A few notes. You'll notice that here I have these separated on lines. You don't actually have to do that. I could have these on the same line. It's just spacing, and all it's going to do is make it look more organized. So it doesn't really matter how you space it, just in terms of the code executing. It's just for the sake of yourself being able to know what you're doing. You can also, if you have multiple input signals that are all the same bit width, you can put them all on the same line like this. And if you have a different bit width, you have to do it on a different line. So here, I'd have to do, if I have a final input D, for example, that's 2 bits, I would have to do it on a separate line, like this. I'm going to go and erase those. All we need for this module is A and Y. At the end of every module, you have an end module. So you can kind of think of the module and end module as being like the curly braces if you were coding in C or in C++. And then we get to the actual meat and potatoes of the module, the actual internals, the hardware. And so what they asked us to do in 3A was to take the input A and shift it left twice. And then we need to sign extend it. So when we take a value and shift it left twice, here's what it would look like. Let's say A was 101. If A was 101, then this value shifted to the left twice would look like this. You just fill in the rightmost spots with zeros for as many times as you shift. So we shifted twice, so we shift in 2 zeros. A sign extension on this new value would look like taking that top bit and copying it over and over and over until we fill up as many bits as we need. In this problem, we needed 12 bits, so I'm going to actually count that. We should have 7 extra ones. 1, 2, 3, 4, 5, 6, 7. 2 extras. So let me just check that. So this 101, that was my original A value. And then the 00 at the end is from shifting to the left twice. And then the extra 7 ones here, looks like 7 ones, that's from sign extending. So now that we know visually what we're trying to do, now we can talk about how to do that in hardware. So what we're doing is we're taking a 12-bit signal. To have a 12-bit signal, all that means is you just have 12 wires running along with each other. That's all that a 12-bit signal is. Same thing for a 3-bit signal. It's just 3 wires running along with one another. And so if you want to put in 2 zeros at the bottom of the number, you just run 2 extra wires along with it that both have the value of 0 on them, or ground. So here's the way you would notate that. These curly braces are the concatenation operator. Concatenation means you just kind of smash them together, and you read it like a single thing. So if I did this, then this would concatenate whatever A is, and then to the right of it, it's going to put 2 bits of binary. So this 2 stands for how many bits we're going, and then I in my head read the apostrophe as bits. So you say 2 bits of, and then the B stands for binary. You could also put hex here if you wanted to, or decimal, or I don't remember if you can do octal, but you can try it out if you want. So I'll do binary for now. Another way of writing this equivalently is like that. This is also another way of saying 2 bits of binary 0, because literally in binary the number 0 in 2 bits is 0, 0. But you could also write it just like this. Either way it's going to understand. So that's how I slap 2 zeros on the end. How do you guys think I can have the topmost bit of A be repeated 7 times to the left? How would I notate that? And then brackets, and then what bit?
The amount of bits that A has, so it could
So I'll write it out. It's going to be, yeah, it's going to be 2. So it's going to be 7. Let me write this out. So we have another concatenation. Specifically, this is a replication. We're replicating one bit 7 times. And the bit we're replicating is A bit 2. I'm doing A bit 2 because that's the most significant bit of A, and that's what we're trying to sign extend. Just for your reference, this inside doesn't have to be a single bit. You can do swaths of bits. You can do ranges. So this, if I had it typed this way, it's going to take the top 2 bits, copy it 7 times, and then throw that at the beginning. However, for our cases, we just want 2. So that's it. That's how you do the module. The last thing I would have to actually write in is I would have to say, I'm going to assign y to be this value. This assign statement is what's called a continuous assign statement. It's just like hooking up the wires directly to one another, rather than having them feed through a flip-flop. So y is going to hold the value of A shifted to the left twice, with it being sign extended 7 bits above. And that is essentially the entire process for this particular module. Any questions? Yes, what's up?
for the A part, don't you want to put like A20?
Excellent question, yeah. So A20 is the entire range of A, right? It interprets that the same as this, so it doesn't matter what you put. If you didn't want every single bit, so you only wanted some of them, then yes, absolutely, you'd have to specify that. But if you want to use all the bits, you can just say that signal.
Both work still?
Both work exactly the same. There's no difference. Okay, so any other questions about that? Okay, so I'll take that as a no more questions. We can move on to part B. So what does part B ask you guys to do?
Name the module detect nums. Y is true whenever the input A is the value 5, 7, 9, or 11. The module should use a minimized SOP equation, in other words, an assign statement to describe this function.
Okay, so assign statement, that's the same thing as we had for module 3A. So now 3B, you said you wanted to name that what? Okay. Now, I'll ask you guys, what are my inputs, what are my outputs? And anyone can answer, Discord or not. Would it just be A? Well, I'd have to look at the prompt, but probably. Let me take a look. Okay, yeah. So what I'm going to do is I'm going to write, what do I write to specify that it's an input signal? What do I type? Do you remember?
Yeah.
Input, logic. And how many bits do I need? Because if it's 1 bit, I don't have to put a bit width here. 4 bits because why? Why is it 4 bits? I think you're correct, but I want to know your reasoning. Yeah. So A has to be able to go up to a maximum of 11. And how many bits do you need to represent the number 11?
Wait, 11?
To represent the number 11, how many bits do you need?
4.
Yeah, 4. So 11 in decimal is the same thing as 1011 in binary. So you need 4 bits, and that's why A is a 4-bit signal. If these were signed numbers, you would actually need 5 bits, because you can't represent 11 in 4 bits of signed notation. Okay, so A is an input. What are our outputs? Or output, if there's just one. And that output is called... Yeah, that output's called Y. And how many bits is Y? It's 1 bit because it's either off or on, right?
Yeah.
It's on when you hit one of those key numbers you said, or it's off everywhere else. So I could, if I wanted to, specify 1 bit of binary, 1 bit signal like this, 0:0, but most people just leave them like that. Means the same thing. This looks arguably cleaner. Doesn't matter how you do it though. Okay, cool. So now what I'm going to do next, again, I'm going to put my end module at the bottom, and then I'm going to say, okay, what is my goal? I'm trying to detect when A is 5, 7, what were the others? 5, 7,
9 or 11.
7, 9, or 11. Oh, that's almost all the odd numbers, or they're all odd numbers, which is interesting. Okay, now we need to write this with an assign statement. So that means we need to derive the logic gates and then write out those logic gates, because it's going to look something like this. Assign y equal to a bit 0, and this isn't the correct answer, by the way, this is just an example. A bit 1 negated, or, and then you continue. So that's SOP form, right? Because that's A0 and not A1, ORed with, and so on and so on. So our final answer for this particular module should look something like this. Now we need to figure out what the formula is. So let's go back to our basics. We're given this task, make a truth table for it.
Isn't there like that's when the I think they call midterm.
Pardon?
Like you call it the midterm. I don't know if it's midterm external, but they have like the numbers within the truth table. So if you're doing 7, 9, 1, 15, ones.
It'll look something like that. That's right. So I'll go ahead and draw it out on, or I'll type it out, what the truth table is going to look like. So I'll do 1, 0. I think I missed one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, cool. So I've written out my A column, and all I'm going to do is I've labeled this in order from 0 to 15. So my Y value here is just going to be whether or not it's going to be on or off, specifically depending on whether or not it's of the group 5, 7, 9, or 11. So for this first spot in the truth table, Y is off, and it's going to be off until we get to the number 5, and then it's going to be off until 7, off until 9, off until 11, and then it's going to be off for the rest of the numbers. So that would be kind of the truth table that we have. And there's a bunch of different ways you can do this. My most recommended method would be to do a K-map, mainly because a K-map is just going to be easier than doing the if you want to form, and Boolean and the K-map guarantees minimized SOP form, so you might as well do it. So I think that's what I'm going to do. Does anyone want me to do the K-map on the board, or do we want to do you want me to just write the actual equation that we get? Because I can go through the K-map if you guys want.
Yeah, can you go through it?
Okay, cool. So I'm going to go ahead and stream the full screen. Okay, cool. And there we go. So I'm going to go ahead and draw up the K-map for the truth table we just had that I have currently shown on screen. And I'm going to go and write that up on the board. I'll be back. I'm going to grab another marker. mechanical engineering students were taking all the good markers. Okay. Okay, any questions for how I set up the key map? And can you see it properly? So it looks good on the camera.
I can see.
Okay, cool. So I've went ahead and set up the key map, and I'm gonna go ahead and fill in the values. So I'm just gonna write off to the side here to make my life easier. Because those are the values we're looking for. Now, up here in the top row and up here in the bottom row, you can mix and match the bits however you want. But for the sake of simplicity, I just made these the top 2 bits and these the bottom 2 bits. So for example, this right here would correspond to 1101. So that would be the number. Well, what would that number be?
13.
Yeah, it would be 13, that's right. So actually this one's off. Okay, so I'll start here. This is the number 0, all zeros, so that's off. And indeed, every even number is going to be off. All my evens are the ones that end in zeros here. So these are all going to be off, and these are all going to be off. Just to make my life a little faster. But we could go one by one and analyze them if you weren't sure. I'll go and look at this one next. This is the number 0001, which is the number 1. It doesn't match, so that's off. We can look at this one next. That's the number 0101. That is 5, and that does match. So that's 5. We can look at this one next. That's the number 1001. That's 9 in binary. And so we keep going like this until we have all our numbers ticked off. So I'll do the next few. So I have 7 here. That's going to correspond to this column. So I have 0111. That's 7 in binary. And then lastly, 11. 11 in binary is going to look like 1011. And if I look for that, that should go right here. So now that I have my my K-map up, I can then do my circling. And in this particular example, it's actually pretty easy compared to some of the ones you guys have done in the past, because there aren't very many options. This guy only has 1 pair. And same for this one. So those are the circles you're kind of forced to take. Okay, and now I can write an equation based on those circles, and I'll ask you guys what the equation is. I'll do the easy part, for y equals. You guys tell me what this bubble is.
It's going to be a bar.
Which bit?
3.
Okay.
A2. A0.
Yeah, that's exactly right. You'll notice in common with every one of these, the bit 3 is always off, so we do not A3. Bit 2 is on, so we do A2. And here, A1 is different in both cases, so we ignore that. A0, though, is 1 in both, so we do A0. Now what about this next bubble?
Same thing, A3, 2 bar.
Okay, now she wanted this in minimized SOP form, right?
Yes.
So we'd leave it as is, no more simplifications. You could actually, though, simplify it. And so just as a quick exercise, what could you do to simplify this a bit?
A0.
Yeah, you can factor the A0 out. That's right. And actually, you can simplify this inside even more. Does this look familiar to anyone?
Yeah.
Yeah, what is it?
With a bar cancels out.
Not quite.
It's one of the, I can't remember, XOR.
Yeah, it's XOR. This is the XOR gate. Remember that XOR is on if the inputs are opposite. This is the first case for when off on, and this is the second case for when on off. So it's the XOR gate. And so in non-SOP minimized form, we can get it down to 1, 2 gates, and it would look like this. So we only have 2 gates here, but for our logic here, we have 2 3-input AND gates and a single 2-input OR gate. So any questions with how I got from this equation down to the schematic down here? Okay, well this schematic is what we want to put on in System Verilog. We want to make this in System Verilog, but you don't have to draw the schematic. Typically you can just go from the equation straight to System Verilog. You don't have to draw it. I was just drawing it to emphasize what we're actually doing. So with that in mind, let's go ahead and write that equation. Okay. Yeah, there it is. There we go. Okay, so for that equation, I'm going to need to plug in my computer here. Okay. It's going to get a little choppy on the Discord and probably in the recording because my computer is low on power, but I'm going to go ahead and start typing up the code for this. So, that one up. Here we go. So what we have first is we need to write out the first term I have on the board over here, which is the A3 bar, A2, A0, all ANDed together. How would I write that? Or how would I type that in code? Yeah, so the negation symbol, remember that we use for System Verilog is the tilde, not the exclamation point. You can use both, but the tilde works on multi-bit signals, whereas the exclamation point does not work on multi-bit signals, so you have to be careful with that. And I can explain that further if anyone's curious. So we have not A3, and then what's the next term? And anyone can answer.
A2.
Yeah, E2, so that's the next term. And then I'm ANDing that with, and what's the next term? A0. Now, if I wanted to, I could space out these ANDs. It doesn't matter. I'll do it for the moment. And now I'm going to be ORing. If you wanted to, you could put parentheses around this entire term just to make sure that you AND before you do the OR operation. But actually, the order of operations that System Verilog uses to parse this is that the ANDs are going to go first anyways, and then the ORs are evaluated. So you don't have to put your parentheses. If, however, these were replaced with ORs, and this was an AND, we would need parentheses, because the order of operations would not be holding according to what we want. So now I'm going to write out the next term. So what would I write for the next term? So I have A3. And then what's the connector I put? Yeah, the ampersand. So I do A3, ampersand, and then what's the next signal? Yeah, tilde A2, or not A2. And then the very last one is what? ampersand A0. Exactly. And so now what I've done is I've taken my truth table, written it as an equation, and then put that equation in System Verilog. And that's pretty much the entire process. That's from the beginning to the end. So any questions about how we got to this point? Okay, so what I'll do now is I'm going to go ahead and we can go ahead and start on part C. And if I recall correctly, part C, isn't it the same as B except you do it with a case statement? Or is it something else entirely? Yeah, oh, okay. Yeah, so you're writing one for and for an inverter and for OR. Okay, cool. So here they want us to make 3 separate modules, one for each of the basic gates. One for AND, one for OR, one for an inverter. So if, for some reason, instead of using the ampersand to do an AND, you wanted a module to do it, this is what you would do. So I'll go ahead and write the first one, and I'll do it for the AND. And I'll have everyone else work on, afterwards, or whenever you want, work on the OR and the inverter. So here's what I'm going to do. Same thing as always. Start with module, and I'm going to call this AND 2. The reason why I'm calling it AND 2 is because it's a 2-input AND gate. So I'm just specifying that. If it was a 3-input AND gate, I would just put AND 3. You can name it whatever you want, but this is what's going to help me remember what it does. Okay, now if I'm ANDing 2 inputs, I'm going to have 2 single-bit inputs. So I'm going to say input logic. And it doesn't matter what I call them. They can be named anything. I could name them in1, in2. I could name them terminal 1, terminal 2, but I'm just going to call them A and B. I'm ANDing A with B. And then similarly, for an AND gate, you have one output. That output is just a single bit value. So I'll say output, logic, and I'll go with Y, because that seems to be the letter we're choosing for a lot of our outputs. You could name it X. You could name it output. Well, you can't name it output. That's a lie. You could name it out1, whatever you want to name it, as long as it's not a keyword like input or output or logic. You can name it whatever you desire. But I'll go with Y. Okay, any questions so far? And let me know if you guys see any typos, and I'll fix them. So the next thing we're going to do is we're going to go ahead and actually code up what an AND gate does. So it's going to feel like, why are we even doing this? And you'll see why in just a second. So if I say assign Y equal to, and then I think, okay, well, I need to AND 2 things. How do I AND 2 things? Yeah, ampersand. I just do A and B. That's the entire module. It's a single line that just says A and B. And it's going to be similar for the other ones, which is why I'm not going to do all of them. I think I believe in you guys enough that you can do them. So that's pretty much it for the 2-input AND gate. I will say that if you were asked to make, say, a 3-input AND gate, you would just have to add in an extra signal here and ampersand with that extra signal. Oops. And so on for more and more. You guys are going to talk about this a little bit. Not too much, but a little bit. You're going to go into parameterized modules. Parameterized just means, let's say that these signals, we didn't always necessarily want them to be 1-bit signals. What if we wanted them to be sometimes 3-bit signals? So we want to instantiate a module specifically for 3-bit signals. But we don't want to write a whole new module, just one for when the inputs are 1-bit and one for when the inputs are 3-bit. So what you do then is you parameterize it, where you put some placeholder n, and it doesn't have to be named n, it can be named whatever you want. And you list that before the port list. So let me go and go over to that. So, I have to put. So here I have a parameter n. And all this is doing is it's saying, hey, currently I have n is 1. And so you can think just in your code, before you place the hardware down, replace all the n's with this. So this is going to end up being 1 minus 1. That's 0:0. And remember earlier I mentioned 0:0 is another way of saying it's a single bit. So with this setup, I now have a one input, single bit input AND gate. So I have an AND gate which ANDs 3 signals together, and each of those individual signals have 1 bit to them. If I instead put n as 2, now each of A, B, and C are 2 bits. So now we are ANDing 2-bit signals from multiple things. And the way that you AND multi-bit signals is you just pair up their least significant bits and go up. So this is the same thing as saying A0 ANDed with A or B2 or B0 ANDed with C0. So that's for the first bit. It's going to produce a second bit. So you can think of it as kind of 2 separate AND gates. And the second bit is going to be A1 and B1 and C1. The only issue with what I have here is that Y has to be the same bit width as the inputs, because otherwise it doesn't have enough bits to hold 1 and then 2 outputs. So I would also have to, in this case, make Y be parameterized as well, like that. Like I said, you're going to go over this a little bit in class, not too much in detail. I'm bringing it up now so that when you hear parameterized module in class, you're not like, what's going on? You have at least some sort of inkling as to what is being talked about. Okay, so parameters, just so you guys know, don't have to be used only for bit widths, but that's typically what you guys will be using them for when you do use them. For now, though, I'm going to erase this because it has nothing to do with the problem at hand. And I'll get rid of this. Okay, so any questions about just the basic module here for AND3? And actually, for the answer for your homework, we're ANDing 2 things. So it would look like this. So I'm going to assume there's no questions. I can let you guys do OR2 and the inverter on your own. Very similar concepts. It's exactly the same. You just replace it with or negation. And I'll move on to part D. Okay, so can I take a look at D? Thank you. So we need to make a multiplexer. Now just to make sure everyone's on the same page, do we all know what a multiplexer is and what it does? We can talk about it. So a multiplexer, you can think of just like a decision maker. So you can think of it almost like a switch. So here's what happens. All multiplexers have a select line. The select line can be multiple bits depending on the multiplexer, because if you have many more inputs than I have here, say you have 4, you need 2 bits of select line. And all that happens is, depending on what the select line is, either A gets routed to the output of Y, so Y equals A, or if select line is 1, Y equals B. And you can think of it being a switch, switching between the two. Physically, that's not what it's doing. It's actual gates, but that's one way to think about it. So it's just a decision maker. And we have to make a multiplexer using gates. So we need to understand what's going on underneath here. So we're going to make, guess what? Another truth table. So let's go and do that. Yeah, truth tables. So let's go and do it. What are my inputs and what are my outputs? And also select line, that's also an input. And then Y is your output. And in this diagram, they're all single bit signals. However, I do want you to know these could be multi-bit as well. The select line still only needs 1 bit to choose between whether or not you're picking A or B, but these can be a huge bus. It can be multiple wires if you want. For this problem, though, it's just 1. Cool? All right. So these are all 1-bit wires. And let's go ahead and write it up a truth table. Now there's a few ways I can do this. I can write down 000, 001, 010, etc., etc., all 8 of them. get my full equation, write it out, do a K-map, and then I get my answer. I'm going to do it a little bit differently from what you guys are used to, just to show you a different way. Cool? So what I'm going to do is the following. I'm going to remove A and B from the inputs. I know this is weird. You're not supposed to know how to do this right now. I'll talk about why it works. So think about what I said verbally. What I said was, when S is 0, Y is A, right? And when S is 1, Y is B. I'm going to literally write that almost word for word on this table. When S is 0, what did we say Y was going to be? And when S is 1, Y is going to be B. Now you might be looking at this thinking, what kind of truth table is this? This looks so weird. Let's derive an equation from this, and let's see if that equation makes sense. Remember that you only pick rows if the output for that row is on, right? So should I pick this row? Why or why not? That's the input. I'm talking about the output. We are going to pick this one, but guess what? We're also picking that one. This one is going to be selected when A is on, and this one is going to be selected when B is on. So here's what I'm going to do. Y is going to be equal to, and let's see, when S is off and A is true, Y is going to be on. And let's think about this. If S is 0, that means we're selecting A, right? And then if A is 1, then Y is going to be 1. So let's plug those numbers in here. If S is 0, this is then going to be a 1. 1 and then if A is 1, 1 and 1 is 1. And that matches up with what we said with our description of the multiplexer. If you hear me say mux, by the way, that's just shorthand for multiplexer, same thing. Now I'm going to do the second one. So for the second one, this occurs when your input S is on, so it's a 1. And when B is on. Now again, let's think about what this is doing. Let's say we select our select line S is 1. What's going to happen to this term if S is 1? This is going to go away. Then S is going to turn into a 1. And so what's left? Would you look at that? Y is now B. If we did the opposite, if we set S equal to 0, the same thing would happen. This would go to 0, so this term is 0, and then this would be 1 and A. And so what we would do is say Y equals A. And now we have our full multiplexer circuit written in one nice equation. Okay, I know that was very weird for everyone, and that's all right. I don't expect you to understand this the first time going around. I just wanted to show you this because this is another way to do truth tables. So, disregarding this, does everyone see why this represents the same as our multiplexer? Because I went through both cases. I went the case of S is on and S is off. So does it make sense that this corresponds to that one? Because if not, I can talk about it again.
I guess when S bar A goes away and it just focuses on
Yeah. So let's say S is 0. Or actually, let's do that one. Sorry. S is 1. If S is 1, what happens to S bar?
0.
What's 0 and A? And that's why it goes away. So this is 0, and then you have 0 or something. That's just going to be that something, whatever it is. Does that make sense?
Yeah.
Okay. Any other questions about that? Okay. Like I said, if you guys wanted to, you could do the full length truth table, all eight rows, do a K-map, and then you will actually get to this at the end once you finish the K-map. It's going to be the same. But what I'm going to do is now I'm going to draw the schematic out. So if I was to dive in here, kind of zoom in and see what gates are present, here's what I would see. So all I've done here is I've said I'm going to send S bar to this AND gate. So S bar and A, that's that first term. And then the second term is S and B. And then you OR them together at the end, and you get Y. Everyone cool with this? Now I'm going to make you guys do some work. You're going to put this into System Verilog exactly the same way we did before. It's exactly the same concept as we did for part, I think it was B, either part B or part A. I can't remember which one we did. B, yeah. So it's exactly the same as B, but for the schematic in that equation instead. So I won't type it up for you guys. I'll have you guys do it. You can do it now, and I'll wait, or yeah, I'll do that. You guys can type it up. I'll give you about a minute to type up this. Yeah, I'll let you type it up. You guys should have told me that I forgot to zoom in. There we go. Sorry about that. Okay, I'm going to guess that everyone's like 70% of the way done around. So just as a reminder, this is a MUX or a multiplexer. You'll sometimes hear me refer to it as a decision maker or decision maker unit. That's because what it does is, depending on this input here, we either decide between outputting A or outputting B. This is a very important building block for things like processors. You use that a lot for when you're trying to decide which signal you want to send out. There are also D multiplexers or D muxes, which go the other way. Where you have one input and you decide which output line to be sending. Very similar concept, just the other way around. You probably won't talk about demuxes until, my guess is 300. I think that's when they talk about demuxes, but multiplexers are pretty important, and demuxes are too as well. Okay, so anyone have any questions about the System Verilog for that?
Quick question.
Yep.
Since with 3 inputs, would it be 3 bits?
So you can code it a bunch of ways. You can have a single bus that has 3 bits, and then you can use bit 1 for this, bit 2 for that, bit 3 for that. That works. Or you can have 3 separate 1-bit inputs, one called A, one called B, one called C. They're all 1 bits. You can do that, yeah. Both are correct. Okay. Yeah, go for it.
I'm sorry. Just a quick question on using like the modules that we created. So we just have to pass in the arguments, right? Or
yeah, great question. I didn't mention this. I'm going to type it up.
Okay.
But when they say use the modules that you've already made, that implies structural code. So I think they mentioned in the problem that it was structural. Does anyone know the difference between behavioral and structural? It's fine if you don't. You might not have been. You might not have heard those words specifically. The main difference is behavioral. That's like gate level design, what we're doing right now. So you sketch out the behavior of it using gates. Structural is you use building blocks like the mux, and then you make something out of a bunch of muxes. That's structural. You're not coding it from scratch, just using gates. And so we're going to do the same thing here. Kind of yes, kind of no, because we're going to be instantiating other modules, but it happens that those modules are going to be ands and ors. So it's a little bit kind of dancing the line between. But I'll show you kind of what it means what it means to be structural. So go ahead and type it up. So that would be 3D. Module mux2. I'm naming it mux2 because there are 2 inputs to the multiplexer. You can have more inputs. You could have 3, 4, 5, as many inputs as you want to your multiplexer. As mentioned before, we have 3 inputs. We have input logic A, B, and S for the select line. And then we have output logic, I'll call it Y. I'm going to do my end module. And I'm going to show you guys how to instantiate a module. So whenever you instantiate a module, it looks kind of like a module declaration here, and you actually use this name. So I'm going to instantiate an AND2 module. So the first thing you put is the name of that module. The second thing you put is the name of the instance. So this can be any name you want. So I could say my AND gate. The difference between this one and that one, you can think of as something like this, int x. This is the type that you're instantiating, and this is the name that you're going to call that specific instantiation. So you could have an int x and an int y. If you're instantiating an AND gate, you can have an AND gate for my AND gate and your AND gate. There are a few rules regarding names you can do. I just suggest playing around with them, but I believe you can't